Thank you. Well, thank you very much. So the first announcement is that actually this is the last of my lectures, and tomorrow morning Ali will start because I think we're all eager to hear about beyond endoscopy, and he has a lot to say, and 6 lectures is more appropriate for him. So today, the goal, so for me to finish up, the goal is to just basically do examples, because last time I tried to present a fairly lengthy calculation. Calculations never get across well, so today I illustrate exactly what that calculation does for GL2. And so I want to do 2 examples basically, and then I want to state Eichler Selberg trace formula, which it was funny because at some point I saw it and I thought, well, you know, this is sort of reminiscent of what we've been doing. It's not exactly. So unfortunately, it's not exactly an example of a calculation I've been presenting, but it's kind of reminiscent of it. And then I talked to Ali and he said, yeah, this was my starting point. And so hopefully he can take this as a starting point. So, all right. So kind of to recap what happened so far is I've been messing with the transitions between different measures. And, well, maybe just a quick summary. So in the trace formula, as it has been stated here, and usually, right, so the measures used are is something like dg dt, where dg is normalized so that locally at every finite place, volume of the integer points of g is 1. And volume of, I'll put something like t twiddle of OV is 1, where by this, I mean, I'd have to be precise about what I mean by this. I think at least I gave an indication last time that you have to be careful how to choose an integral model, and it's not automatic to say what you mean by the integral points of the torus. But at almost all places, this is pretty automatic. So roughly speaking, this is what's happening, right? So, and so in particular, and with this good reason to use this normalization of measures in the global trace, in the trace formula, because with this normalization, as we will see in a very explicit example, but generally that's what you expect, that for almost all finite places, the orbital integral is 1. Local orbital integral is 1. And so that means that the global orbital integrals are finite products. So at least you don't have to worry about convergence, and this is a very reasonable thing to be doing in the trace form. So that's what we have on the one hand. On the other hand, we could take the measures that are very related to this. I'll call this something like d omega g mod d omega t. So again, these would be the measures normalized by taking invariant differential form. So again, it's a quotient. The key point is that it's still quotient of a measure on g by a measure on t, but both come from invariant volume forms. And finally, the measures that one would like to wind up with is what Frankel, Langlands, and Go call the geometric measure. Is something like d omega g mod d omega a, where this is now a quotient. So this is where somehow conceptual leap happens, because now you don't care to normalize measures on the tori separately. You actually just treat stable orbits as fibers of the Steinberg map. And so this is this Steinberg-Hitchin base. This is my representation of it. And so this omega A is just the affine space measure on the Steinberg-Hitchin base. And so then you get the measure on orbits treated as fibers. Right, and so now just, so the conversion factors that appear here, so here you just pick up a constant. So maybe I'll do it in different color. So this is where you pick up a factor of, well, the volume of the maximal compact here was 1. Here it will be whatever this differential form gives it, and it turns out to be the number of points of G over the residue field locally times Q to the minus dimension of G. That's what you pick up from renormalizing G. And from renormalizing T, you pick up the number of points on the reduction mod P of that smooth model of T of FQ, mod Q to the minus dimension of T. And this, if you wish, this can be written as a ratio of Artin L factors. At 1. So I think I wrote down an example last time for this one where it became the Artin L function. Well, I mean, we will see it again, but it was the Artin L function attached to a quadratic character of a torus in the case of GL2. But so anyways, here you just pick up something that depends, well, on G and on the torus, but does not depend on individual element. And here, you pick up also a factor. So if you want to go all the way, you will pick up both. But here, when you're doing this transition, you pick up a factor of the discriminant of gamma 1/2 or negative 1/2, no, just 1/2, sorry, without the negative. Well, depending on which way you go. So here, gamma is our element of G over the local field, and D is the Weil discriminant. And this was kind of a calculation that got a little bit rushed last time, which is basically the same calculation as in the Weil integration formula, but done twice. Okay? Is this roughly, so I think that's where we are at right now. So maybe a quick moment for questions. Okay? So all I wanted to do for now is show a couple of examples, one in GL2 and another even simpler. So the second example will only refer to this part, kind of indicating what it actually means in terms of the filling for the objects that you're dealing with. Just what does it look like in a calculation? So the first example is GL2. And so there you can actually use the tree to compute orbital integrals. So I'm not going to go into that. An excellent exposition is given by Kotovets in his Clay volume. So, but I will write down the answer just to give us a sense for what the orbital integrals are like. So these are going to be, so I'm quoting Kotovets, his expository notes. So, well, we introduce an element, sorry, we introduced a number d gamma. So suppose gamma is a regular elliptic element. So this d gamma is the evaluation of 1 minus E1 over E2, where E1 and E2, I'm now switching to Tasha's notation, are eigenvalues of gamma if, so this is in the case, if gamma is split or unramified. meaning its eigenvalues live in an unramified extension. So if ramified, the definition of this d gamma is more complicated. So this, you can write it, there are various unpleasant ways of writing it down. I can write one. So it's the supremum of the valuations in E, the extension that's generated by the eigenvalues of gamma minus A, where A runs over the ring of integers of the base field. So, but one way or another, what it comes down to, one can compute that it's really just half the valuation of the Weyl discriminant, essentially, except it has to be an integer. So it's so what you have is that the V absolute value of the Weyl discriminant is q to the minus 2d gamma in the split or unramified case, and q to the minus 2d gamma minus 1, I think, if ramified. I'm hiding a lot of unpleasant calculations, and I could have made a mistake by plus or minus 1, but I hope I did not. So, and a little bit of the meaning for this d gamma, the way it comes up in the calculation that Kottwitz presents, is this d gamma really is the it's a number. How to say this? It's the integer such that you can interpret the set of fixed vertices under the action by gamma as the set of vertices whose distance to the standard apartment is not greater than d gamma. So, so this Weyl discriminant can be interpreted here in terms of kind of geometric terms if you're doing calculation on the building. For those who do not want to think about the tree for GL2, just don't worry about this at all. So I'm just saying that in this particular case, GL2 is one of the very few cases where orbital integrals have actually been computed on the nose, and the calculation on the building actually works. Doesn't get too complicated so that you just get some estimate or something. And so, so here we understand everything, and it turns out that we see explicitly this half of the, so you can just take the definition of d gamma to be this. So if you don't like the building, just think of this as definition of d gamma, and we can compute an orbital integral. And I'm just saying that half the valuation of the discriminant turns out to have this interpretation. So, so this was just a parenthetical remark. But okay, and so then in this situation, the canonical orbital integral, and you will see in a moment why this business is a little bit frustrating. So I'm just going to write down the canonical orbital integral of the characteristic function of the maximal compact. Kottwitz gives formulas for the whole spherical Hecke algebra, but I don't particularly care. And I'm going to, oh yeah, so here I'm everywhere assuming that gamma lives in the ring of integers, and it lives in the maximal compact. Well, partly because if I'm computing this orbital integral, then if gamma is not conjugate to any element here, you will get 0. And so then you might as well take gamma to be here. So, okay, so it turns out, so here's finally, we see an orbital integral, so it's simply q to the d gamma if gamma is split. 1 plus q plus 1 times q to the d gamma minus 1 over q minus 1 if unramified, and 2 times q to the d gamma plus 1 minus 1 over q minus 1 if ramified. So this is what you would read in Kottwitz. Notice this 2 is very unpleasant. So, and that's because even Kottwitz in this note does not quite specify which measure he is working on when gamma is ramified. He's very precise for split-end and ramified, and then mumbles something for ramified gamma. And I think this is not exactly the canonical measure, so it's like, I would put something like canonical over 2 or something like that. There is this matter of what do you, which model you take, and I think that index 2 shows up there, and in Kottwitz's note, it's not what we would call canonical right now. So I think if you wanted canonical, the 2 disappears. So, however, I mean, if you read Kottwitz, you see that, and for me, this is the definitive reference in a way, because nobody else wrote down the explicit calculation for these orbital integrals. So anyway, I'm just going to ignore the 2. All right? And so notice a couple of things. So in Tasha's lectures, I think he called the eigenvalues E and E bar because he was talking about elliptic elements. Oh, yeah, sorry, I said, it's silly. Okay, sorry about that. So I wrote it down for all, but I mean, we care for elliptic eventually. So, yeah, so Tasha's eigenvalues were E and E bar, and remember there was this factor that showed up of absolute value of E minus E bar. Notice that this is basically the same thing if you're close to the identity anyway. So that was, well, what Tasha was doing was renormalizing them by the square root of the discriminant so that they don't become so big. Notice exactly, so yeah, maybe the lesson to be learned here is that as this valuation gets large, so which means that our element gets close to being non-regular. Yeah, so maybe I will make this remark in writing. So the example illustrates the theoretical principle that we know from Harish-Chandra. So note if d gamma is large, so gamma is close to being non-regular, right? That means that eigenvalues get close together. Then O gamma of this function becomes approximately of the size d of gamma to the 1/2. Negative. Right? And so the discriminant gets close to 0, and the orbital integral gets close to 1 over the square root of the discriminant. So that's kind of exactly what you would expect from the behavior of orbital integrals. Okay? And so now I'm supposed to renormalize these, so just tell you what you get with our renormalization, taking all of these factors into account. Okay, so we normalize them all the way to here. So and so what we get is that O gamma geometric of the characteristic function of the maximal compact is this discriminant to the 1/2 times the number of points So I've computed these two things last time, so I don't feel so bad about using it. Okay, the global discriminant, so E is the quadratic extension corresponding to T. So I discussed this factor last time, so I don't want to go back, and so O gamma canonical of the same function. Okay. And so when you put it all together and multiply this by the Kottwitz formula, you wind up with, I think, 1 + 1 over Q when gamma is split. Always. And one minus 1 over Q times some stuff. I mean, I don't know if you want to copy this. I don't know. I mean, I'll put this in the printed notes. I just want to illustrate what this thing looks like. So this is the unramified. And I think it winds up being something like this: q squared minus 1 over q squared times q to the minus d gamma, q to the d gamma plus 1 minus 1 over q minus 1. Okay, if ramified. So the thing to note here is what happens when d gamma is 0, right? So for almost all primes, so basically there are two reality checks that one wants to see. So, so if d gamma is 0, we get 1 in the split and unramified cases. Oh, sorry, no. Misspoke. So we get 1 here, right? If d gamma is 0, we get 1 here and 1 here. And that's our canonical orbital integral, which is 1 almost always. But here, we get, in the split case, we get 1 minus 1 over q. I'm making a mistake. No, maybe 1 plus 1 over q, sorry. And in the unramified, we get 1 minus 1 over q. Right? So this thing starts looking like you're getting some kind of L value. So these things, so now you have to worry about convergence, right? So this is, for canonical measure, the orbital integral was doing fine. Now you wind up with a product that conditionally converges. Yeah, so this would be the geometric measure. So when you do the orbital integrals with respect to the geometric measure, suddenly, because of all the factors that went in, you wind up with only conditionally convergent products sometimes. So you have to start worrying about convergence. So it's kind of unusual. And as my next example illustrates, so yeah, that's kind of the only note I wanted to have. And now I want to do an even simpler example. So I cannot, unfortunately, do it for you for GL2 in any finite amount of time, and maybe not even quite in the lecture notes. Some things don't work. But here I'd like to offer kind of a very silly illustration on how some of these factors that we picked up encode some arithmetic invariance. And so in some ways, orbital integrals also repackage the same arithmetic invariance, but maybe in a different way, if you look at everything locally, right? So every local component of an integral, of an orbital integral, will contain some piece of this local L value. When you put them all together, you will wind up with an L function, but there are class number formulas, right, which basically tell you that you could repackage things differently. And so I'm going to discuss something that's probably familiar to a lot of people here, but if not, then I think it's a good exercise to do. And it's just the class number formula. And you will see more complicated class numbers in the Eichler-Zilberg case, and I think there you need a bit more calculation than what I've presented. So, yeah, so the next part of what I wanted to talk about is revisiting the simplest case of the analytic class number formula for an imaginary quadratic extension. And if you're like me, working with p-adic groups, then you probably completely forgot what this thing is. But on the other hand, I think everybody knows. So, okay, I'll write down the general class number formula for a general number field. So, and then lots of factors will disappear. Okay, so here K is a number field. And okay, and so this guy is its class number. Okay, this is the discriminant that we've already seen. This is omega k is the number of roots of unity in K. S is the number of real embeddings. And 2T is the number of complex embeddings. Okay, and now, okay, RK is the regulator whom I'm not going to define because it's going to disappear. It's going to be 1 for an imaginary quadratic field. We don't care for it right now. Well, so who is the zeta? Zeta is the Dedekind zeta function. Okay, so in our case, a lot of this disappears, so it doesn't actually have a pole for an imaginary quadratic field. It's fine. And so you don't need this limit. You don't need the regulator. And so you wind up with, so our case is K imaginary quadratic. Another piece that I'm going to skip is that it turns out that zeta K is the same as the L function attached to the quadratic character of K. Which is, remember, we had this before, so it's at primes is defined by 1 if the prime splits, -1 if P is unramified, and 0 if ramified. We saw this exactly when we were computing volumes of tori. This will come up again. Okay, so, okay, and so then what we get from this class number formula is that L of 1 chi is 2 pi times the class number over the square root of the discriminant and over the number of units. Okay? So fine. Now the point is that I'm going to use this to illustrate that this whole formula is just a volume calculation. So we've already discussed kind of the proof of its formula in disguise. So, yeah, so my claim is somehow both sides calculate the same volume. And so this is where some of the stuff that we already discussed shows up. All right, so what volume? So, well, recall a strong approximation, sorry, weak approximation for Q. Actually, I just need weak approximation. Yeah. So if I take finite ideals and take this double quotient, right? So, I mean, it's silly to write it as a double quotient. The thing is commutative, but I'll write it this way anyway, right? So this is just 1 for Q because the class number of Q is 1. Normally, you would expect for an imaginary quadratic field, you would expect that this would be something like the class group, but it's not exactly because of the intersection with the units. So let's write down what we actually have. Is it a thunderstorm? No? Okay, so, well, what we have is, So if we're careful about this kind of quotient, right, so I need to take care of the intersection of the product of all the units with k cross. Okay, so I can do this, and that maps to finite ideals mod k cross, and that maps to the class group of k. Okay. And so now the point is that if I assign these guys volume 1, so that means I'm thinking of the canonical measure, so to speak, right? So then the volume with respect to the canonical measure of this gadget is going to be the class number. Oh, yeah, I should have said this. So this, right, it's you want to be a unit locally at every place, and at the same time you want to be in K. So these are precisely the roots of 1 in K, right? And so, so then what we get is if each of these components has volume 1, right, then this exact sequence gives us that the volume of this guy is going to be this divided by the size of the kernel. All right. So now the point is that I think what we've done, well, so now recall that K star is nothing but the set of Q points of the restriction of scalars from K to Q of GM. So this is our kind of torus that corresponds to K. So we've seen this guy, right? So this is a torus corresponding to K in GL2 over Q. So we know how to locally compute its volume with respect to the measure that came from a differential form. So this would be, I had on this board this two-step measure conversion. So here we don't have any Steinberg-Hitchin base. We don't care. Everything is commutative, right? But we still need to get from the canonical, so to speak, volume to the one that comes from a differential form. And that's what we're doing. And so okay, and so locally, so volume with respect to this differential form on the torus, well, I'll write it dx over x, roughly speaking. I have to do pullback if yeah, so this is exactly the calculation I did last time, I think, and so it winds up being 1 minus 1 over p times L of 1 chi inverse, right, times the discriminant of kv to the 1/2. So this is the computation we did last time for the volume of this torus. Which is this restriction of scalars. Okay? So I think this is exactly what we computed. And so great, and so we just put these things together. So yeah, now a key point that we need to remember is that, well, there is a matter of the Tomogawa number as defined by Wei, and it's the volume with respect to the measure adjusted by the convergence factors. So these guys get killed when passing to the Tomogawa measure because they are the convergence factors. I mean, convergence factors are inverses of them. So remember, these guys anyway came from the center of, well, I mean, our torus is not exactly an isotropic. It has a copy of GM. This is where this came from, and we're killing it. And so what we get, yeah, and so there is a key fact that we need to know. is that Tomogawa number, which is the volume, by definition it's the volume with respect to a measure came from a differential form but adjusted by convergence factors. As discussed, so for general group, you take its adelic points over G of Q. Okay, and so here it's all adels, I mean, not just finite adels. What I mean is you need to keep track of the infinity component. So, okay. And so the key things that we need to know is that the Tomogawa number of GM, so yeah, maybe this is called the, well, and again, okay, I gave a slightly simplified definition of the Tomogawa number here, kind of assuming that G is an isotropic mod center. I'm going to just skip that. So anyway, so we'll call this guy tau of G. I'll put approximately this. So anyway, so what we need to know is that the Tomogawa number of GM is 1, and it's also preserved by restriction of scalars. So for this torus, it's also going to be 1. So these are just facts. Okay, so knowing these facts, so basically I'm trying to say that the class number formula for this case is exactly this fact repackaged. So right, because now what we get is the following thing. So what we get is that the volume with respect to this Tomogawa measure of, for our torus of T of the adels mod T of Q equals 1. So after we've killed the GM part, what's left is, well, let's rewrite it in the following way. So this would be the finite adels times the R points of this torus. So now, I'm lying a little bit, but if you kill the GM part, then what you're left with is a unit circle. So the reasonable thing that you get here is the 2 pi. That's where 2 pi is coming from. And so after just a little bit of lying about this, we get so now let's see what's the difference between the Tomogawa volume and the canonical volume. Well, at every place, instead of 1, you pick up this, right? So what we get is the product of all the local factors at 1 chi inverse over V finite times delta kV to the 1/2. So this was what came out of our measure conversions. Well, times 2 pi, this is coming from the real place. I'm shuffling something under the rug a little bit. Okay, and then times the canonical volume. So the whole thing is 1. And so that gives us, if you take, so this is L of 1 chi inverse, you take it to the other side, recall the product formula for the discriminant, that if you want the product of all the p-adic places is 1 over the actual real absolute value, and you're done. Any questions about this? So again, I am showing this calculation just to illustrate how all of these arithmetic invariances, well, this is sort of, you could say that the class number is purely analytic invariant, and the volume is, is purely arithmetic invariant, and the volume is an analytic thing that you can compute, and they're all, of course, tied together by formulas like this, and ultimately held together by Tomogawa volumes. And a lot of this stuff, so this and this is what we see disappear kind of when we're doing the conversion of the measure to the geometric measure. And the discriminant disappears too. So in some ways, you could expect that the whole thing would look a lot simpler than the original canonical orbital integrals that are so notoriously hard to compute. Okay, and so finally, the last thing I wanted to say is just state Eichler-Selberg trace formula and kind of discuss how it's similar, what it corresponds to in the Arthur trace formula that we've seen. Okay. Any questions so far? All right. So Eichler-Selberg is a formula for the trace of a usual Hecke operator Tn, kind of classical modular forms Hecke operator on, say, Sk, the space of modular forms. So, sorry, I'll say, so cusp forms of, and think classical modular forms, right, of weight k. And for simplicity, I will just take level to be 1. Right now, just to write less. Okay. So the Hecke operator. Oh yeah. So maybe say this. So Arthur trace formula is inequality of distributions. So here we're going to think of this Eichler-Selberg. So it is kind of a special case of Arthur-Selberg trace formula. For GL2, when we apply it to a specific test function. So the Arthur-Selberg trace formula is inequality of distributions. We're going to choose a test function basically that gives the nth Hecke operator on the space of weight k cusp forms. That's the idea. And so let me write down the formula and then explain where it all comes from. So this is our trace, and it's k minus 1 over 12 times. I'll write this as 1 squares of n. So this thing is 1 if n is a perfect square, and 0 otherwise, plus, what am I doing? No, sorry, one more thing here, times n to the k over 2 minus 1. No, not plus, minus 1. Okay, I'll write this down and then define all the notation because it's a bit notation intensive. Oh, it's a long formula, so it's nice to have a long board. Okay, so maybe it'll fit now. So it's sum over m Okay. All right, so now who's who in this formula? So here, rho and rho bar that appear are roots of the polynomial x squared minus dx plus n. And this h sub w, so this w stands for weighted. So this is kind of the most interesting piece. So it's the so-called class number of the order in Q rho, which has discriminant So I will not define this in detail, but we'll discuss it in a moment. And W stands for weighted, so weighted by the size of its automorphism group. All right, and so, yeah, I think at this point, yeah, at least I've defined all the notation. And so, yeah, what I wanted to say in the last few minutes was maybe just a bit of a discussion of how this indeed is a special case of Arthur-Selberg trace formula, even though it doesn't quite look like it. So, first of all, just sort of to get oriented, so this is going to be the contribution of the identity. So yeah, what I should say is, as you probably guessed, I mean, this whole thing, we're looking at the geometric side. And so this is contribution of the identity conjugacy class. This is the elliptic orbital integrals weighted by the corresponding volumes in disguise. And this is the hyperbolic and unipotent group together. Sorry? Yeah? Oh, sorry. I think no, I think it's the. No, do you get this guy, or am I wrong? You shouldn't? It's possible that I'm making a mistake. Well. Okay, I'm going to leave this with a question mark. Actually, I didn't think of this at all, so I'm sorry. So this, I just thought we'd shove these things under the rug for now and just look at the elliptic part. But so I think Ali will say more. So, well, I think in general, so Ali said that this is his starting point, or was when he started working on it. So the point was to start with the trace formula, right? And then first you have to isolate the identity contribution. And then you do something on the elliptic part and at least make it look like something on the Steinberg-Hitchin base. And this is kind of halfway there. So I'm trying to say that it's not exactly what you would get when you really do everything I've discussed to the Arthur-Selberg, but you get kind of some ways towards this interpretation. And it's not clear if this is exactly the right thing to do because it doesn't generalize all that well to other groups. So anyway, in the last few minutes, maybe I discussed that. So, and then, yeah, I just decided to just shove these things under the rug, so I'm not so sure about what happens to the unipotent term. By the way, I should point out that there is a book by Knightley and Lee. It's a pretty thick book, which basically does this. It starts with the Arthur-Selberg trace formula, and it ends with this, and defines everything in the process. So I'm obviously not going to do exposition of the whole thing, but yeah. So, all right. Anyway, so what we want to say is, yeah. So first of all, what's the test function, right? So. Well, so the point is that the test function we want to choose is, so of course it's going to be f infinity times the product, oops, of finite ones. And so f infinity is going to be, of course, well, you could take the complex conjugate of the matrix coefficient of highest weight of the discrete series of highest weight k, where k is the weight, right? And so if you do that, then that will ensure that everything else other than the weight k cusp forms gets killed. And so that gives you an operator on the right space. And now if you want to have the nth Hecke operator, then, well, since level is 1 here, so the fp are easy to define as well. So if p does not divide n, you basically want to take the characteristic function of the maximal compact. Oh, sorry, it's ZP in this. Everything is happening over Q right now, so it's just ZP. But, okay, so you have to somehow take care of the center. So I'm not sure this is the best way to do it, but anyway, so in Knightley and Lee, they put the center of QP here. And if P divides N, that's when you want to take, well, if you want nth Hecke operator, right, then it's summing over, I mean, it would correspond to something that came from matrices of determinant n, right? So what you want to take is the sum of the all double cosets in G of QP whose determinant has valuation n. So I'm going to write it briefly as M of n. So this is the union. I can write it this way. So it's matrices M of ZP intersect with the set of G of the determinant. Valuation of the determinant is n. Okay, times the central part. Okay, so and so now what's going on in here is, so just to highlight what's happening in this formula, so this is coming from, so this is the orbital integral, oh yeah, sorry. First of all, what orbital integrals of which elements? So this sum is already written as a sum over the Steinberg base, right? Because it's a sum over traces. So, so Tn determines, yeah, and we only care for elements whose valuation of the determinant is n, because otherwise the orbital integral would be 0 of the function that we care for. Okay, so the Tn is a point in a Steinberg-Hitchin base. So this is already orbital integral. So we expect that these would be the orbital integrals written kind of in this new form. So this is the component, the infinity component, because if you take the matrix coefficient, take its orbital integral, you basically get the character, and this is these characters have sort of, I think this is the beginning of the Gelfand-Grave formula for the p-adics. I mean, for the reals, you can compute it, and this is what you get. And so, okay, and so now what about this? So I think so these class numbers. It gets more complicated when, so let's see. When you look at this characteristic polynomial, so characteristic polynomials of semi-simple elements are exactly polynomials of the form x squared minus tx plus n, right? And so if you look at an element with this characteristic polynomial, if the discriminant of this polynomial is, has p-adic valuation 0, then there is nothing interesting going on. Then this d gamma would be 0. And in that case, you get the actual ring of integers of this field. So then nothing particularly interesting is happening. And so I think what I have already done in secret is I think we see how the orbital integral times the volume of this T of A mod T of Q equals this class number. So in this case, this class number is the actual class number of, what did they denote it by? O of rho, right? So this is just the ring of integers of the, it's like Z of rho or something. So it's the ring of integers of our quadratic extension. So I think our calculation does sort of amount to this so far, more or less. But I have not shown how what these class numbers generally mean when you have a non-zero valuation discriminant. The calculation, so it's interesting, if you look at Knightley and Lee, maybe just one last word about it, unfortunately, they prove it by direct computation, and the computation very much parallels the computation of the orbital integral on the building. So you kind of see that these things have to come out to be the same, and it's just a repackaging of the orbital integral into the class number. Modulo the factors, some L factors that come from this volume that are hiding in the conversion of the two measures. And so it's a very suggestive thing. And the last thing I want to say about it is that, so it's a calculation, but it's a suggestive calculation. And Givet-Youn generalizes this. I don't know if he started with Knightley and Lee or just wrote it down by himself. But Givet-Youn has a similar calculation for GLN. Expressing orbital integrals as class numbers, which are very much like this. But Givet says that his calculation does not generalize to other types. I'm not so sure. I actually think that it should generalize, but I don't actually have a formula. I was hoping to have it by these lectures, but I don't. So yeah, anyway, and so I think that's a good place for me to stop, and hopefully Ellie picks it up from there and explains what magic he can do with that beyond endoscope. Thanks. Yeah. Oh, yeah, sorry. So, yeah, so Givet-Youn, he has, I think it's about 2013 or so, he has a paper maybe, so some Dedekind zeta functions and orbital integrals. I think these terms appear in the title in some order. I'm not sure. But the word Dedekind zeta function shows up. And so he expresses orbital integrals in GLN as the value at 1 of some Dedekind zeta function, which is very much like that. It's kind of suggestive. Well, he says it cannot. I mean, I'm thinking about it, so I'd be happy to try and talk about this if you want. But I don't know yet. So I'm not ready to vouch for it cannot be generalized. Maybe it can, but I don't yet know how. Yay, thank you.